Welcome to Session 4 of the ESIG 2020 Fall Technical Workshop. The workshop is being held online on Tuesdays and Thursdays during the month of October and into early November. I'm Charlie Smith, the Executive Director of ESIG, and I'll provide a few brief opening remarks. As with so many things we were planning to do in person this year, our plans were derailed by the coronavirus, and here we are online again. The workshop was planned with the input of our ESIG Offerings Committee, chaired by Bethany Frew of NREL and Julia Matoibasan of ERCOT. The committee consists of the chairs of our 6 working groups and several of our board members. We have a great set of volunteers who make ESIG what it is, and we encourage you to become involved if you're not already. Regarding logistics, I would like to ask you to note that the webinar will be an hour long. We will have 3 individual presentations of approximately 10 to 12 minutes each, and we plan to hold the questions for a 15-minute Q&A session after the last speaker. As we're doing with all of our webinars now, we'll be using the Slido platform for managing the Q&A. We would ask you to use Slido for your questions, as you will not be able to ask your questions through WebEx. You should go to slido.com on your device and enter ESIG8 as the event code to ask your questions. Please be sure to indicate the person to whom you're addressing the question. The instructions are also in the background slide for the webinar, and you'll be reminded by the session chair. You'll see a thumbs up button next to the question on Slido to allow you to vote on prioritizing the questions submitted. So please keep the questions coming during the presentations, and we will address them at the end. Recognizing the limitations of a webinar with typically more than 100 people on the lines will be muted. So again, we ask you to use the Slido platform to ask your questions with ESIG8 as the event code. Session 4 today deals with a very timely topic these days on hydrogen production and flexibility requirements. We will hear several different angles on this topic from Europe, Australia, and the US. The session will be chaired by Mark O'Malley of UC Dublin, with Jason MacDowell of GE Energy Consulting serving as co-chair. Mark is a well-known figure in the energy systems integration space, chair of our Research and Education Working Group, and a leader in the Global Power System Transformation, or GPST, initiative. Jason is another well-known figure in the industry and the chair of our Reliability Working Group. Both Mark and Jason are good friends and regular contributors to ESIG activities. Mark and Jason, we appreciate having you here, and I'll now turn it over to you, Mark.
Okay, thank you. So welcome everyone to the session. So I'm Mark O'Malley. This session is about hydrogen, which Charlie mentioned. We actually have 2 sessions on hydrogen in this conference, which shows you the growing importance of it. And one of the slides I wanted to show myself at the very start, Bryan, can you just throw up that slide? I just thought this was a very appropriate slide to introduce this session with. You know, Exxon briefly dethroned as America's most valuable energy company. In fact, as far as I know today, they are the second most valuable. The first most valuable is Yara, essentially a renewables company. I think that the world stock markets is trying to tell us that, look, liquid fuel from carbon sources is going out of business, and we have to find a replacement, and I think hydrogen is possibly one of its replacements. So without further ado, we have 3 speakers, as Charlie said, Australia, the US, and Europe. We're going to run them in reverse order to the way you saw them in the pictures. We're going to start off with the US first, and then because Bryan Pivovar of NREL, a former colleague of mine, is going to be giving a high-level view, research view, where it's going. And then our other 2 speakers are going to be talking about applications. So Bryan, I checked your name out online before we came on, and apparently Pivovar means brewer. So Bryan is a brewer of hydrogen. Bryan, it's over to you.
Thanks, Mark. It's my pleasure to speak to you guys about Hydrogen at Scale, which is a U.S. initiative. It reflects a lot of the other initiatives going on across the planet in hydrogen. And I'll just start with happy Hydrogen Day to everybody. I don't know that most on this call would recognize that October 8th is Hydrogen Day. It's much like Pi Day, which is the 14th of March for 3.14 for the value of pi, Star Wars Day, which was May the 4th, like May the 4th be with you. And Hydrogen Day is basically October 8th based on the 1.008 atomic weight of hydrogen. So I'm sure that most didn't know that today was International or U.S. National Hydrogen Day, but it is. And so it's my pleasure to be speaking to you about hydrogen today. And what I'm going to talk to you about is basically how the world's changing and how hydrogen is a key part of how the world's changing. So here, I just like to throw up a slide that has select relevant megatrends. One is the falling costs of renewables. You know, and these low-cost renewables tend to be intermittent electrons, and so there's a challenge with that. And they only service one sector, basically the grid, typically. And then there's a bunch of energy policy and a bunch of increased electrification. Even urbanization is another trend that pushes towards hydrogen. And then what I like to talk about is that, you know, there's some policy things that are going on, and there's basically the wildfires, the storms, the air quality, the loss of reefs. There's a bunch of different environmental drivers for why this is becoming more important. And then the economics are also improving to the extent that make it a much more viable pathway. I like to use this slide, which is getting a little dated now, but basically talks about what's happened over the last decade. And I often refer to the 2010s as the decade of wind and solar. And I joined NREL around 2008. And what happened shortly thereafter was this precipitous drop in the cost of wind and solar. And that's led to this really large increase in capacity. But there's a limit to that because it's an intermittent resource and it doesn't do everything you need it to be. And that's where hydrogen starts to come in. And what I tend to talk about is this hydrogen at scale vision. And it's kind of highlighted in this slide where on the left-hand side, you have kind of the energy sources that we use to drive our planet, things like renewables, nuclear, fossil fuels. We have these large infrastructures like the grid, like the natural gas transmission system, and also hydrogen can parallel each of those. Now, hydrogen can take some of these inputs on the left-hand side, like renewables or fossil, and directly create hydrogen. Or it can take the electricity that's being driven by those, make hydrogen through electrolysis. And it can take things like fossil fuels directly, make hydrogen from the natural gas, or hydrogen can actually be turned back into natural gas. And then on the right-hand side, I basically show all of the different things that hydrogen can do. And this is really where the cross-sector coupling is important. These light blue areas are areas of transportation. The purple are areas of industry. And they're the hardest to decarbonize and make clean and efficient. But hydrogen does this well. This red dot at the bottom for heating is basically just for thermal energy, which is also used a lot of times in industry, but also for buildings and other residential purposes and commercial. So overall, it's how hydrogen can couple with what we have and how it can enable the shifts in the system, because some of this renewables on the left-hand side has a lot of time dependence to it, and hydrogen allows it to be stored and transmitted over different areas to address that. So usually after I show this kind of vision, what I like to do is I like to talk about the attributes. And what's really becoming clear is that this cross-sectoral and cross-temporal ability of hydrogen to store and move energy is becoming really critical. But also hydrogen's critical because of how clean and efficient it is in its end use. So both of those things together are huge attributes of how hydrogen fits. And why, if you're only looking at one area, like if you're only looking at the grid or you're only looking at transportation, you don't always come to hydrogen as being a critical piece of it. When you look energy system wide, hydrogen has much larger benefits. And those benefits include things like economy. There's a lot of jobs and GDP impacts. Also, because you're dealing with local renewable resources oftentimes there's an enhanced energy security. But really, a lot of times it is these environmental benefits that are the main drivers. And from my perspective, getting all of these benefits in a single energy system is an increased value proposition as well. This is starting to become really well seen across the globe. You can see things like a hydrogen roadmap for Europe or for Japan. The US has one. I'll talk a little bit about the Hydrogen Council, but basically this cross-sector coupling and the need for clean energy is a big driver for where hydrogen fits. And the economics have been changing so that the differential cost for being able to do this has become less and less as time's gone by. The Hydrogen Council is one of the most important entities for championing hydrogen. And so I like to talk about them a lot. It was started only really 3+ years ago by 13 members, and the companies that are on this list are all going to be well known to everybody on the call. And you can see that today it's gone, from 13 up to 52, today 92 members, all kind of Fortune 500 types of companies, all included in the energy system, a lot of the big oil and gas companies. And they've gone out, and in 2017, they came out with a roadmap that was across the planet that basically said by 2050, they predicted 2.5 trillion in global revenues, 30 million jobs, and 18% of all total global energy demand would be connected to hydrogen. In the US, you can see how hydrogen's changing as well. There's over 0.5 gigawatt of stationary power. If you run a distribution center for Walmart or for Amazon, you run it on fuel cell powered forklifts powered by hydrogen. There's buses. There's almost 10,000 cars in California, and there's big pushes to do things that light duty vehicles that are powered by batteries can't do well in the heavy duty transportation space. Because of the increased energy density, because of refueling times versus recharging times. And so hydrogen exists today, it's growing more and more, and that's not changing as we go towards the future. This past November, there was a US hydrogen study and roadmap that came out, and this is, again, you can look at these companies. These are, a number of these companies are associated with the Hydrogen Council. And they basically said in the US, it's going to be, $750 billion in revenue and 14% of US energy by 2050. And this is because the economics of energy aren't balanced across the planet, but it's very consistent with the global study that was done for hydrogen as well by the Hydrogen Council. So the scale of hydrogen and what we expect hydrogen to become in the future is really large. And it's not just academics or national labs that are talking about it. It really is these major industries in these areas that are recognizing what's going on in this space as well. At NREL, we're doing things that are trying to understand what the future might look like and also how to enable it. So here we can see things about what we project kind of 2050 levels of hydrogen to be used. And this report actually came out last night just in time for Hydrogen Day today. And so I'd be happy to provide a web link to this. But we talk about how hydrogen, regardless of what happens in terms of different scenarios, is going to become more prevalent in society. And if we can do some things like enable low-cost electrolysis, that it'll be much more enabled, and it will also be made in a more green process. So these are only economic arguments, and they don't have any policy or societal drivers outside of it. So even just from an economic perspective, hydrogen is going to be used more, and I can talk more about why that is. And we also do things like, how would you move this energy around? So this is one of the maps that I love. It basically talks about the great wind resource we have in the center of the country, and how if we build hydrogen pipelines, we can take that hydrogen out to the coasts where most of the energy in our country is consumed, and basically economically distribute that hydrogen and that wind energy from the center of the country to actually drive the economy in the outer parts. There's a lot more detail in some of these reports that would follow up with this detail for the attendees. But a lot of it does come down to how expensive it is to move energy. So this is basically the cost to move a megawatt hour of energy 1,000 miles. And what you can see is that electricity lines, they are very expensive to move energy, and they also are limited in that they don't have any storage capacity. You compare this to oil pipelines, which is a really dense form of fuel, ethanol or methanol, which are slightly less dense liquid fuels, and then natural gas and hydrogen, They're both much cheaper than electricity. Hydrogen has some incremental cost increases compared to natural gas, but it's not very far off in terms of a distribution cost. It's just that this is projecting an infrastructure that we spent all of the money on to allow the natural gas to be stored and transported, whereas hydrogen doesn't have that. So if we look towards the future, we can move hydrogen almost as economically on an energy basis as we can move natural gas today. The other place that the economics come in, and this comes down to electrolysis. So if you talk about electrolysis, on the far right side here, we have SMR, which is steam methane reforming, and this is the way that hydrogen is made today. And so typically you see $2 per kilogram as a US target. In Europe, because natural gas prices are much higher, and that's the green part of this $1.95 number, and a gallon, this is basically a kilogram of hydrogen, which is a gallon of gasoline equivalent. Only when you use hydrogen in a fuel cell vehicle, you get about twice the mileage out of it. So somewhere between $2 and $5 per kilogram often is quoted as a cost target for hydrogen, depending on its use and depending on the economics of the area that are largely driven by the cost of local natural gas. And the question is how do we get the economics of electrolysis cheap enough to compete with steam methane reforming? And this graph kind of highlights it. So today what's going on is this $4.20 per kilogram hydrogen, which assumes that we're basically scaling up today's electrolysis technology, and we're kind of taking expensive electrons at 6 cents kilowatts per hour. And the premise is that in the future, we're going to have much lower cost electrons available. And if we talk about only being able to use those electrons 40% of the time, so the rest of this data is for 40%, whereas this first bar is assuming a 97% capacity factor. At 2 cents and 1 cent per kilowatt hour, just by intermittent integration, we can take today's technology and become much more cost competitive between $2.25 and $2.75 a kilogram in hydrogen. But then you see that instead of this green area where electricity is a dominant cost today, this cheap electricity basically means that now we're concerned about the capital costs of the electrolysis systems. And if we make these electrolysis systems cheaper, and we basically say we're willing to give up some of the efficiency, 10% of the efficiency, to make these systems much cheaper, we all of a sudden can see how you can make hydrogen less expensive than steam methane reforming and start displacing the vast amounts of hydrogen that are being produced today by green or renewable hydrogen potentially. And so this is kind of the direction that things are going. This R&D Advances is part of a new consortium that I serve as director for at NREL, which is called H2New, which is how you basically allow these systems to act intermittently at lower costs. And with that, I'm going to pass it on to our following presenters, but welcome you to follow up with me with anything that I can help with.
Okay, thank you, Brian. So we'll wait for questions till the end. So please put your questions into Slido. ESIG is the code. Our next speaker is Michael from Denmark. He works for Ørsted, which used to be, I think it used to be Dong, which is Danish oil. And that, again, it's an appropriate history. Dong was I think the Danish oil and natural gas company. It became essentially a renewables company, and now they're looking at hydrogen. They've gone full circle to some extent. So Michael, over to you.
As said, my name is Michael, and I have the pleasure of speaking to you about the Green Fuels for Denmark Project Vision, which is a project centered around the Copenhagen area in Denmark, which aims to decarbonize heavy road transport, marine shipping, and aviation at one at the same time. But before we dive into the project specifically, I just want to make some general points about a general rationale for why we pursued the direction in the project that we have, and take you through that journey, basically. So if we look at emissions overall on a global scale, of course, a significant proportion of that comes from electricity and also heat. Electricity has experienced rapid decarbonization over the past couple of years. There's definitely some way to go yet, but it's quite clear that we have the technologies available, and I think few question which direction it's going to go. I think it's the question, or the solution rather, is not so obvious within, say, transportation and industrial applications where decarbonization, frankly, has not really progressed much over the past couple of decades. And it's really within this area that we believe in Ørsted that hydrogen and power-to-X applications more generally have a role to play, because they give us the opportunity to indirectly electrify these so-called hard-to-abate sectors that have really been untouched in the green transformation. As said, we previously came from a very oil and gas heavy industry, but had transformed into a pure play renewables company, mostly focused on offshore wind, but also have a position within solar, PV, and onshore. With regards to hydrogen, we think that there's a really good match between offshore wind and electrolysis for three reasons, basically. The first one is scale. So currently the biggest offshore wind farms being commissioned are bigger than 1 gigawatt in the Lego building blocks, if you will, that we're constructing them in. And that's important if you're looking at applications like new ways of producing steel or refineries where you would need very big electricity sources to serve those demands if they are to change to renewable hydrogen. Secondly, you have the capacity factor. The overall, you could say, headline of today's session is about flexibility requirements. And while there will definitely be intermittency within offshore wind generation as well, on a macro scale, though, you have the electricity available a lot of the time. So this graph says 43, but on some of the good sites, you actually have capacity factors in excess of 50%. So that actually matches quite well with somewhat baseload generation, if you will. So that, together with the cost of electricity, of course, results in your levelized cost of hydrogen. And the third argument for offshore wind is really the resource availability. So if you're in the US or if you're in Australia, you benefit from having a lot of onshore potential, but in more densely populated areas. Offshore wind really is the only electricity source that you could realize at scale and sufficient scale to meet the energy input demands required for the full decarbonization. Basically, hydrogen can be used for almost everything, but our belief is that industry applications and heavy-duty transport really are the most promising ones. And that's the key reason for that is that there are few alternatives to producing steel or producing ammonia going forward if the premise is that we need to reach net zero emissions by some date. Quite frankly, there's not enough biomass resources available to really address the energy needs of some of these sectors. So if you look at it from that point of view, from a resource potential, then hydrogen and P2X seem like the choices that you need to, or rather the technologies that you need to choose. You could use it for turning electricity into hydrogen for the sake of heating buildings. Our view is that there are better and cheaper alternatives, such as heat pumps out there, that one should use instead. Rather do electrification directly, if possible, rather than go through intricate solutions like hydrogen for those sectors. But even so, there's still an enormous potential for hydrogen and P2X. That was the same rationale that we basically took when developing the Green Fuels for Denmark project. That was basically launched in response to Denmark coming out with a binding emission reduction target of 70% by 2030. So the project consortium members basically took a look at that and said, well, given the situation of Denmark, where there's not a lot of heavy industry, almost none, what levers do we need to make use of in order to get to a 70% reduction by 2030? And taking a look at that, we came to the conclusion you can actually go very far with known means: heat pumps, battery electric vehicles, a bit of biofuel blending, etc. But even so, if you implemented all those in a very bullish scenario, you'd still be left with some a residual that you needed to address, where it would be meaningful to address it through P2X. And if you look even further beyond 2030, the rationale for P2X becomes even stronger in a Danish context. So basically, on the back of that, the companies that you see here, which might not be so well known to you, but are very well known in Denmark, these companies got together and defined a vision to establish large-scale renewable fuels production in the greater Copenhagen area, with the aim of decarbonizing the various sectors that these companies represent. Basically, the intention is to over 3 phases, develop a facility with an electrolyzer input of 1.3 gigawatts of electricity that will produce roughly 30% of the fuel quantity used in the Copenhagen airport. And secondly, it will have an outlet of fuel for the marine shipping, sector, and also for heavy duty road transport in the greater Copenhagen area. So for road transport, it's going to be pure hydrogen for fuel cell based transport. For the marine shipping, it's likely going to be methanol, and for aviation, it's going to be a synthetic kerosene. The basis for the project is illustrated here. So even though we don't exactly know the route we're going to take to kerosene, basically we are adding carbon to the hydrogen in order to produce fuels that are relevant for marine shipping and aircraft. The reason why these companies got together, and they are fairly different, I would say, is that at the center of this you have electrolysis. So all of these companies, both from a regulatory point of view, but also from a project point of view, benefit from scale and benefit from the same regulation that is spurring demand. So for that reason, we have scoped the project to cater basically for all at one at the same time. And for that reason, we are focusing for the downstream on a carbon-based fuel, because that is what is required for long distance aircraft travel. The intended electricity source for this is a large offshore wind farm in the Baltic Sea. And when we talk about intermittency, it is quite important, at least in a European context, that the hydrogen you produce is correlated with the electricity asset that you have in order to qualify and meeting green standards. So you need to balance your supply obligation together with the availability of the electricity source, really to make a product which is truly green, which provides options also with regards to secondary income streams like ancillary services. But also because of this flexibility, you have the opportunity to be turned off by the TSOs, so that in case the electricity system is overloaded, they reserve the right to basically load shift some of the load that you're putting onto the general system in exchange of lower grid tariffs, so you generally get electricity at a lower cost. I would end up by saying, well, while we're very keen on the project, we are not quite there yet. So it's a bit like building a car while driving it. So in order to really make this happen, we're in parallel working on improving the framework conditions, both on the production side, but also on the fuel offtake side. So currently, there are no strong incentives on the fuel consumption side. but it's key basically that the offtake demand is stimulated in order for this transition from fossil to green to happen. And with that, I'm going to hand it over to the next speaker. Thank you.
Okay, thank you, Michael. Our next speaker is Luke from Australia. So Luke, over to you.
Yeah, look, I guess by way of introduction, and I think hopefully we're on the journey, if you like, from the broader sense down to something relatively narrow. So I'm going to talk about an isolated project, and I think the key for all of you and the roles you hold is to consider the implications, I guess, of the kinds of changes you'll see out there in the manufacturing sector, where significant energy consumers are going down a pathway that's quite significantly different to where we've been going for a century plus, and the impacts of that. So some of the particularly relevant aspects of what we've heard already today include Bryan's slide on hydrogen at scale. Particularly relevant there is some of the things we'll see around the cross-sector aspects of what we're doing. Our journey also is reflective of the electrolysis cost pathway that Bryan discussed, and something that Michael just mentioned around the geographic siting I think is so critical. So I guess we'll jump down to a fairly specific example of what you're seeing and the implications. I'll step through fairly quickly here, just in case my American friends aren't actually fully aware of Yara. We're just a part of the great Norsk Hydro conglomerate, if you like, until a few years ago, with over a century of operations. And being from Norway, where our major shareholder in around 40% is the Norwegian government. So our actions to some extent are reflective of the broader European/Scandinavian discussions around power, renewables, etc. And so I guess that's interesting from the point of view that it's certainly a different perspective to the energy discussion in Australia, and also I think from the US. Again, this slide is just to illustrate as major consumers and producers of energy, where Yara, as an example of one of many large private sector entities, is seeing the future. And I mentioned briefly earlier in an email, President Xi Jinping has announced that China's aim is a 2060 deadline to be carbon neutral, which is an interesting claim to make, and clearly has the ability to start making significant moves in that direction. So we're looking at the world's largest emitter by a significant amount, setting up just a few decades whereby they'll become carbon neutral. So I think the implications of those discussions in the private sector, in the broader policy settings, are very significant to the global energy market, production, etc. This is, I guess, the nub of what it is that we're doing at Yara, what many of our competitors and other industries are looking at. If you look at the dirty brown bottom path, stem methane reforming was mentioned again earlier. So you can see here that we basically use a very large amount of fossil fuel, natural gas in our case. The key, I guess, hydrogen's often seen as a novel chemical or feedstock or whatever in so many ways, and certainly as a major energy source, hydrogen is novel. But for Yara and many others, particularly in the chemical feedstock and fertilizers, manufacturing, etc., hydrogen is already a very significant element of what we do. And so it's something we produce, something we consume, something that we handle on a daily basis. So many of our discussions with regulators, government departments, etc. in Australia, one of the key elements is, of course, the safety or social license aspect to large-scale hydrogen, which we form a part of. Then if we step up to the green, this is, I guess, a business as usual to some extent for us. That is, we continue down the same path of doing what we do. The only change is that very initial front end changes from a fossil fuel input and steam methane reforming to renewable energy, splitting water via electrolysis and producing our hydrogen in that manner. So beyond that point, the process is precisely the same. The products are precisely the same. The interesting element in this discussion and in so many others is the potential for a green hydrogen market, which currently basically doesn't exist, and then a similar change for ammonia to become an energy carrier. The best way to understand that is we've used hydrogen to make nitrogen available in the agriculture sector for well over a century. Now we're potentially seeking to use nitrogen as a potential to make hydrogen, the energy from hydrogen available in other areas. So effectively, just as LNG is liquefying the gas to make it economic for scale and export, similarly we'll be using ammonia to ship effectively hydrogen molecules overseas. So those considerations are there. But as a first step, we're focusing on changing the production of existing facilities. This, I guess, is this slide's we recently presented in Japan to a major conference, and I guess the key point here to look at is for power generation. Japan has a stated ambition around 2030 to effectively flip their economy to hydrogen-based, and that was going to be a major trumpeting, if you like, of the Olympics that were to be held this year. So we'll have to carry that over to 2021. But what you're looking at for a country like Australia, that's already a very, very big energy exporter to Japan, largely through LNG, is that by 2030, Japan won't have any interest in our LNG anymore. It'll be looking for green hydrogen. And so that quite clearly gives us some interest in new markets, etc. And so one of the early starting points, there's a major green ammonia consortium in Japan, would be looking at renewably generated ammonia from northwestern Australia being utilised in Japan for power generation. So again, the hydrogen role there is indirectly going into direct combustion ammonia in the power stations which are currently burning coal, etc. So again, hydrogen is a significant element of the future power generation in Japan. There's also the pursuit of regasification, and there's all sorts of discussions around the various energy loss, etc. But this, again, as I mentioned, is where ammonia is cracked. The hydrogen shipped with as a component of ammonia. That's then cracked at the other end, just like an LNG regasification terminal. And the nitrogen can obviously be emitted into air. And so you effectively ship the renewably generated hydrogen from northwest Australia into the Japanese power sector. So that's a key focus for many within the Australian government and private sector. Just to give you the context of where we operate, and as I said, this project to some extent represents a very isolated example. So you may at first be thinking there's not a lot of relevance to the power transmission sector, etc. But what you'll see is even in the most isolated part of the world, the pursuit of renewable hydrogen is potentially impacting the energy sector in Western Australia significantly. So Karratha, where I've highlighted there, is around 1,000 miles or 1,500 kilometres from the nearest city, which is Perth, down the bottom left-hand corner. It is actually, though, a very significant energy location for the nation of Australia. So this is just zooming into a portion of the Pilbara region. It's one of the most irradiated areas of the world geographically. And so what you're looking at here, interestingly, is around 500,000 square kilometres or about 190,000 square miles. So an area bigger than California, but a population of only around 60,000 people and a vast sunshine irradiation virtually every day of the year. So we also have a very significant wind resource available. We're in a close proximity to export markets, as I mentioned before, existing energy export markets. And interestingly, there's multiple major private sector entities pursuing emissions reduction and or renewable opportunities, which I'll show you briefly in a moment. So this is the specific location here. So what you're looking at is Yara has the sites at the bottom right. You see on the left an ammonia production facility, on the right an ammonium nitrate facility. So some pretty energy hungry operations. We produce around 800,000 tonnes per annum from that ammonia plant. And so obviously to make that, we already produce around 140,000 tonnes per year of hydrogen and consume that. And so therefore you're looking at already a major production and consumption of hydrogen. That also takes in at the moment through steam methane reforming around 80 terajoules a day of natural gas. So we're taking around 10% of the input for the natural gas pipeline, which runs basically outside our front fence here. What you're also seeing here is in the top section is 6 LNG trains in total with an export capacity of 21.8 megatons per annum. And they're also supplying the DOM gas into the Dampier to Bunbury pipeline. So the pipeline here runs for 1,500 kilometres, around 1,000 miles, and that provides 21% of the power generation in the state of Western Australia. So that's producing around 845 terajoules a day. An interesting aspect there is that this pipeline, they're already conducting a feasibility study of up to 10% hydrogen injection there from renewables. So I'll touch on that a little later. This is, I guess, the key slide. And it's not to consider this project in isolation, but I think to extrapolate to your own environments of what might be the impacts of these sorts of levels of both generation, power and production of renewable hydrogen and the impacts on power systems, etc. And also look particularly at the time frames. So potentially by 2030, which is in most people's horizons, we'd be looking, if you add them up, to a total of 2 gigawatts of new power generation from a renewables base in an isolated part of Western Australia, and producing again an additional 800,000 tonnes per annum of ammonia from renewables base. So in the other element here is referring to my earlier slide, is that we'll also have massive amounts of hydrogen available. That can, of course, be sent off for energy use, as I mentioned, into the pipeline, or we can, of course, further process it into the ammonia, which, as I mentioned, can also be used for direct combustion or a source of hydrogen and exported. So it's also worth noting, as I mentioned, that 2030 timeframe for major renewables production here in Western Australia roughly aligns with Japan's timeframe for major changeover to green hydrogen. And I think that's one of the interesting elements, as you'd be aware, in the hydrocarbon space. There's a lot of interest from various players. ExxonMobil's been mentioned. BP has taken significant steps. They're seeking to decarbonise their operations, which is almost an oxymoron. But our local major independent producer, for instance, Woodside, is pursuing 2 renewable hydrogen projects and talking about ammonia export, despite never having produced a molecule of hydrogen or ammonia in its 50-year history. And so people and entities in the private sector are piling in with excitement to this area. And so the implications, I think, will be significant. Just to mention this, I think it's important because Australia's justifiably seen as not exactly leading the debate around renewables. We're one of the most per capita intensive emitters in the world, and yet, can I say it, even in Australia, we've developed a fairly significant national hydrogen strategy developed by the CSIRO, and importantly, that was developed by the Council of Australian Governments, which represents all state and the Commonwealth, meaning that you've got effectively a unified national approach to how we'll approach hydrogen entering our energy sector and everything else. We also have in Western Australia, given our pretty extreme isolation, our own renewable hydrogen strategy, which sets out some specific export aspirations, etc. And just the final slide I'll flick to, and I guess this brings it all together. There's a mix of proposals in here of various levels of maturity. So, for instance, our project in phase 0 prior to the 1, 2 and 3 major scale-up is a 10 megawatt project, so 10 megawatt electrolyzer, 23 meg of solar PV. We may be taking FID as early as Q1 of next year on that. We've got environmental approvals, we've got the land, we've obviously got the offtake in that the 800,000 tonnes we're producing of ammonia already. We can add in another 1% based on renewables. Another one, which I mentioned briefly, is the project here listed as preparing transmission pipelines for H2. So the owners of that 1,000-mile pipeline from which we draw natural gas will be completing next year a feasibility study into 10% hydrogen injection into what has been for 35 years, a 100% natural gas pipeline. And they own infrastructure Australia-wide. So you're seeing the potential for hydrogen injection up to 10% as a first stage into our natural gas network. Another one there that's mentioned is the Asian Renewable Energy Hub. That's a 15 gigawatt proposal of solar wind integration, and they have 6,500 square kilometres available. So that could change not just the energy dynamics of our whole region, it could have an export capacity as well, and they're seeking to start construction in 2026. So we may become off-takers of power or hydrogen from them. And again, it's just changing the whole energy mix in Western Australia. And as I say, potentially they could become a Japan, China, Singapore, even India exporter of renewables for power. Another interesting aspect is that just one of the iron ore miners in Western Australia, FMG that's mentioned here, they currently use around 600,000 litres or 160,000 gallons of diesel per year on their mine sites, and they are extremely bullish about changing over their entire fleet to renewables. And so again, they'll be taking themselves off the standard grid and isolating themselves via renewables. So again, there's an impact there on the whole system. I guess the key to take away from this in the broader context is in your own environments to consider the partnerships and value that will shake out from the various opportunities that are being explored in the private sector with strong government support, because we'll find alignment with various of these players along the way and find some abilities to scale up, and the economics will improve. So there's very interesting and challenging times ahead for us all. Just the final point is that we received funding from the Australian Renewable Energy Agency, and so they'll be publishing our feasibility study in the next few days, and so that will be available on their website. So I'm certainly happy to send that to the organisers. So there'll be around a 40-page document that will be available on our project, which also obviously talks about opportunities elsewhere. So I'll finish up there and thank you very much for your time.
Okay, thanks, Luke. Jason, over to you.
Great, thank you, everybody. 3 great presentations from Bryan. And I'll pull up the Slido. A lot of questions. I think we've got about 15 to 16, but certainly about 15 minutes to go. So we're not going to be able to get to everyone, but let's go down by the popularity here. The first one is actually not addressed to anyone in particular. Maybe we can kick this off to Bryan or perhaps Michael. Can the electrolyzer provide ancillary services by quickly turning on and off, ramping up and down? In other words, what are the benefits that can be gained in terms of flexibility from the latest electrolyzer technology? Great. Yeah, go ahead.
Basically, ancillary services are very simple for electrolyzers to take on. We have a system that's been integrated, and a lot of different ways show that they provide the basically like a spinning reserve, and typically throttling up and throttling down happen at rates that match the energy system's needs. So it's not exactly clear how much stress that puts on the electrolysis system and whether or not you'd want to mitigate those times, but they will provide dispatchable services as well. Typically, the economics of doing so aren't as valuable as the other economics of the hydrogen, the value of the hydrogen produced, but it is another value stream that they provide.
Great.
If I may add on that.
Sure, Michael. Please.
Typically, the manufacturers that we've engaged with, they see no problem in turning up or down within 30 seconds, and sometimes even less, even if it's alkaline-based electrolysis. And PEM, of course, is even more flexible. And typically, that serves the needs of most ancillary services products. So generally, equipment manufacturers are fine with that. Definitely there is an opportunity to provide ancillary services, but it's a secondary revenue stream. I agree with Bryan on that part.
Great. The next question goes specifically to Bryan. Bryan, do you think that $100 per kilowatt electrolyzer capital cost is feasible? And what's the technology that can best achieve that? Is it PEM, AEC? Can you make some comment there?
Yeah, so I don't know if $100 a kilowatt is achievable, but we feel that $150 a kilowatt is likely achievable, and that $100 per kilowatt may be achievable. At about $200 per kilowatt, the economics start to look very compelling for a lot of these things. And a lot of it does depend on what happens with the rest of the energy system. So the whole H2 consortium focuses primarily on PEM because it's the near-term technology. Alkaline should be able to do it as well, but it's not clear if the throttling aspects and the differential pressure aspects of alkaline are going to have the same capabilities, but from a cost perspective, alkaline should only be cheaper than PEM. And then there's other choices, even like solid oxide, which even have a larger struggle with throttling hot on and off because of the hot and cold cycles. But we're looking in areas where you could potentially couple them with nuclear plants or do other types of hybrid systems. So regardless of the technology you're talking about, $100 a kilowatt is going to be a challenging target. But we think that $200 a kilowatt is going to be happening sooner rather than later. At least $150 a kilowatt will happen, and potentially $100 a kilowatt can happen.
Okay, thank you, Bryan. Next question, let's go over back on safety concerns that we might have with hydrogen production use, and maybe how things have evolved to tackle some of those safety concerns.
I think one of the major safety concerns is, well, for the Green Fuels for Denmark project specifically, generally if you're developing these projects before you have hydrogen pipelines that are capable of distributing the hydrogen from far away, you would tend to build these projects where you have demand. And in the case of the Green Fuels for Denmark project, you would like to get as close to the fuel off-takers as possible. And that is a challenge, especially in a city like Copenhagen, where you have a lot of residential areas. So if you have a 1.3 gigawatt plant with hydrogen, large amounts of hydrogen storage, of course, you would need to do very, very detailed analyses of the likelihood of an accident and what that accident would imply. So I think to go back to the central question, that would be on the production side, specifically with the large amounts of hydrogen you would have available, because you would need to store some of it on a buffer basis in order to have your processes run smoothly, especially when you have to combine it with a chemical synthesis loop afterwards that might need more stable processes than the electrolyzer in itself.
Okay, yeah, thank you, Michael. The next question, I'd like to get one in here for Luke as well. We've got one actually addressed to Michael and Luke. Maybe we'll start with Luke first. How much loss of efficiency and additional cost is there in producing products like ammonia and syngas? I apologize. We lost our feed here, but if we'll start with Luke and then transition to Michael.
Look, I think the key is I don't have specific figures to put up for the question directly, but I think the key to focus on here is that what we're looking is this, if you like, precipitous drop in the price of the electrons, and so particularly in our area, there is no question that the large scale availability of the renewables makes these issues less and less of a concern. And some of the other entities we're having discussions with, for instance, they quite clearly see a premium for, particularly in these early stages, to catalyse the market, a premium willing to be paid. So whilst we need to factor in those extra costs, the markets that need to effectively decarbonise due to government policy, etc., are willing to pay above. And that's what's being pursued in the next few years. But as I say, with the very steep effectively availability of large amounts of cheap renewable power in locations such as ours, that additional cost becomes less important than the capital cost of the projects that we're getting up.
And if I may add to that, I think you can buy a commercially available pressurized alkaline electrolyzer today that has a high heating value efficiency of slightly below 75%. So that is, of course, quite efficient. But if you have to go all the way to jet fuel, I think state-of-the-art processes will not get you above 50% efficiency currently, and one has to be aware that you need to pay for capturing the carbon from a CO2 source on the way, which of course would add costs in addition. So the cost will definitely rise quite rapidly the further you go towards more and more complex molecules in the chain. So to put it short, the more you can do with hydrogen directly, the better. But there are certain applications where that is just not an option due to lack of energy density.
Yeah, thank you, Michael. The next question that has quite a few votes has to do particularly with green hydrogen around electrolyzing and the needs of the feed of water. How clean does the water feeding the electrolyzer need to be, and is that a significant cost? It's not addressed to anyone. Does anyone want to take that? Perhaps Bryan, you want to start?
The water has to be basically deionized by the time it goes in. So there's a processing cost that shows up in this. And I talk about the $2 a kilogram as a cost for target for the hydrogen. And the water costs tend to be on the order of a couple cents per kilogram, maybe 2 cents a kilogram. So from a cost perspective, it isn't a significant cost, but it has to be done.
On cleanliness of water and supply of water for electrolysis? Okay, let's move on to the next question. Actually goes to Bryan as well. I wanted to get thoughts on electrolysis from solar power, let's say in the Southwest. Your map showed in your presentation electrolysis for wind power, but why not the curtailed solar power?
So there's a lot of detail in that map that I glossed over. And there is solar from the Southwest in that map. It just doesn't show up because it uses the pipelines that are there. And the main reason that it looks like it's predominantly wind from the Midwest is because it's the cheapest on a per electron basis. And so it was just an economic rollout of what the cheapest cost way to deliver that was going to be. However, depending on local drive, without kind of any policy or local drivers engaged with it. So the ability to do this by direct solar coupling is absolutely clear, and it's even perhaps it can save some money because it's a DC to DC technology where you can actually size things like your electrolyzer to match the solar generation site. So solar works just well. It's really just the economics of the electrons that push that specific example to the wind in the U.S.
Time for one more. The next one on the list is really not addressed to anybody. It's to all the panelists. Are any of the presenters aware of any operating combined cycle power plant that is now burning hydrogen instead of natural gas or distillate? Okay, I think that's a short answer. If no one wants to take it, I think the answer is that the presenters aren't aware of any. Go ahead.
I'm not, but I would say that they are starting to burn blends, and every major turbine manufacturer is looking to go for 100% pure hydrogen as well as mixed blends. So there are a number of new projects. One is in Utah where there's salt domes to put the hydrogen into, where they're doing blending of hydrogen and natural gas. So what's really happening is the first step is kind of these blends, which Luke talked about at some level, and then the next step might be more direct hydrogen.
Great. Yeah, thanks. I appreciate that, Bryan. I guess we're wrapping up the hour. Maybe one more very quick question, and I'd like to maybe hand that to Luke because we haven't heard as much from Luke yet. Luke, in your presentation, could you quickly explain why ammonia and not synthetic gas that you were using?
Sure. I guess the key thing here is like everything, you're not wanting to have significant alterations to existing capital investments. So ammonia is a product that we know and ship and is safe, And so we're utilising that on a daily basis, exporting hundreds of thousands of tonnes a year. And so from a relatively conservative stepwise change in what it is that we're doing, ammonia is the product that we're most comfortable with. And I think that goes to a whole range of issues, including the safety issues, the fact that there's an existing market, existing consumption, etc. And so what we'll see is, as we saw, a 1% change in our input. Next step will be between 6 and 20% based on a range of factors, and then we're looking at 60 to 80% change. And along that way, we may well explore alternative pathways. But given the lack of existing market for renewables in this space and the existing premium and cost differential, we're taking an incremental change away from what we do. And ammonia is what we do, if you like.
Yeah, great. Thank you for explaining that. Okay, I think that rounds it out for the time we have today. We had over 20 questions, and unfortunately we were able to not get to everyone, but we'll do our best to round out the remaining questions with the panelists and get back to you. So Mark, I'll hand it back over to you to close us out.
Okay, Jason. So thanks to all our panelists and to Jason. It was very interesting. I think we're going to hear much more about hydrogen because it's, well, I mean, the message I took about this is hydrogen is now looking like it might be in business because the renewables are cheap. So I think the renewables have actually stimulated the hydrogen business. And not only that, but I suppose the renewables business needs the hydrogen. So there's a nice symbiotic relationship going on there. There is one more session on hydrogen. I think it's this day week in the ESIG agenda. There's another 8 sessions altogether. I'd encourage you to go to ESIG's website and register for them. They'll be going on from now to early November. And the next one is about, I think it's 24/7 clean energy is on next Tuesday is the next one. So that's it for us. Stay safe home, go to work, go home, wherever you are in the world. And thank you for attending. Goodbye.